Okay, so let's continue with our topics. So last time we have discussed, let me summarize what we have discussed last lecture. Low-pass equivalent of a bandpass, let's say, signal. So this was the topic of last time. So what do I mean by this? Well, in the spectrum, let's say that x of f, this is the frequency spectrum, I have a bandpass signal in this bandwidth, meaning that, let's say that it's in triangular shape, symmetric around this, let's say, spatial frequency f naught. Okay? But it's a bandpass signal, it's not occupying the DC frequency, but it's occupying a non-zero center frequency, let's say. This is the center frequency. Okay. So since this is real valued, and since this is the magnitude spectrum, so we are expecting that, let me draw this bigger. An even function for the magnitude response or the magnitude spectrum of the signal. Now, of course, if you check this, the spectrum is almost always zero except this part. Okay. So the information content in this signal is located in this, what we call the bandwidth. Since the signal is real valued, if I know this part, I can also say everything about this part. So the low-pass equivalent is essentially, you would like to shift this part only, okay, to the origin. So you would like to make this low-pass. So how can I do this? There are two steps. Now you get rid of this negative frequency part. Once you get rid of this negative frequency part, the remaining signal with the non-zero values at the zero and the positive frequencies, it's called the analytic signal. You may remember, it's very important, analytic signal. Then you have only this part, then you move it to the origin, that becomes the low-pass equivalent. So in these steps, there's like multiplication by 2. I will further explain, because you will see. Then once you move this to the origin, the peak amplitude will not be after this movement to the origin of this part, essentially. It will be 2a instead of a. This is already in your notes. So today, we are doing something very similar and easy, actually. Representation of bandpass systems. So this was signal, now system. Representation of bandpass, let me write LTI systems. So let me write a bandpass LTI system has a frequency response h of f centered around a non-zero frequency. Like exactly as in this case, but it's not x of f this time, it's not the input. This is the system, as you see. Our goal is to find the low-pass equivalent of such a bandpass system. Okay. So how can we do this? So let's remember, so if I have x of t, if this is h of f, then this is y of t. Okay. So clearly I'm interested in bandpass signals and I know how to represent this bandpass signal. So this is bandpass, let's say, system or filter, LTI filter, and this is the output right now. Okay. This is the output. So how can I deal with this? So let me have some sketches. So the first sketch. So this is x, x of f. Let me do this one more time then. If I have a, again triangle shape, let's say f naught, bandwidth, let's say f naught, bandwidth, but minus f naught. So this is the magnitude spectrum, let's say. This is the peak values A. Okay. Now, we have studied this. If we say that the Lowpass equivalent of this one is, so x Lowpass equivalent, again the magnitude. Okay. So it's actually the same triangular shape, the same waveform. I don't want any distortions because it should be capturing the value or the function in this spectrum, okay, in this bandwidth. So this is the same bandwidth around 0. This is low pass, but the issue is right now this is 2A. Okay, if this is right now, A is over here, just to mention it. 2A is somewhere over there. Okay. Now this is what we know. This is about input. So let me do the same thing for h of f. So let me sketch this. H of f is, let's say, flat over here, just for the sake of simplicity. Okay. It's an ideal bandpass filter, let's say. So its level is at B. This is the same bandwidth. Maybe center frequency f naught again. Okay. This is with respect to the frequency f. Okay. So this is again a bandpass signal, but about it's the impulse response. Impulse response of this filter when Fourier transformed, I get this. So what's its Lowpass equivalent? Well, the same story. So the thing is, if this is B, I need a 2B over here. It's a little larger. So this is the Lowpass equivalent of this. I'm drawing it larger. So this is the same bandwidth. I think it's enough about bandwidth. This. Okay. Okay, let's mention it. This is the same bandwidth. Okay. So what is, now forget about this part. Forget about this part. Now, if I have this convolution relationship between output and input, now what is y of f? So it's multiplication of these two. Am I right? The output is x of f times h of f. So in magnitude, these magnitudes will be multiplied. So if I do this, I get this triangle shape, but the peak value will be, some a times b. Am I right? I mean, that is the case. So let me have this. So this is the AB. So this is also a bandpass signal. So if I sketch this, now this time it is the same. I should get 2 times AB. Okay. So what am I using over here? This knowledge of Lowpass equivalence. For deterministic signal, this is its Lowpass equivalent. This is a deterministic impulse response in frequency domain. This is Lowpass equivalent. So these are the Lowpass equivalents of the signals. Okay. Very trivial. Now, what is the question? So this is, let me write this, y Lowpass output equivalent of this. Now I claim y Lowpass equivalent f is equal to h Lowpass equivalent f times x Lowpass equivalent f. Is it the case? It's not the case. So how can I correct this? There is a trivial correction. Divide by 2. Excellent. That's divide by 2. Because this is the reason that I have these sketches. Well, if I multiply these two, maybe I should write this 2b. Okay. B becomes 2b. If I multiply these two, I always get 4ab, not 2ab. Okay. So in order to have this equivalency of the y's, okay, I need this 1 over 2 factor. So explanation, I think it's this explanation. The 1 over 2 factor above, I think it's very clear, but is needed since in the generation of low-pass equivalence, we have multiplication by 2 in the bandwidth of interest. Am I right? Therefore, let me write this. On right hand side of this equation star, I have 2 multiplications by, let me write this like 2 multiplications by 2, and I need to cancel one of them with 1 over 2. One of them. But I think it's very clear from this explanation. Okay, this is what we do. So if I give you low-pass equivalent of the channel, let's say, or the system, low-pass equivalent of the input, then you multiply them, but don't forget 1 over 2 if you want to get the low-pass equivalent of the output. That's the case. So let's erase this. This is not a claim right now, but essentially this is our fact. Okay? So this is the case. What else? Now, this is good. So our next topic is, this is our final topic of the course. Okay. So we would like to representation of, let's say, bandpass Y-stand stationary processes. Okay. Now, previously we have studied signals, deterministic systems. Now, Y-stand stationary processes. So let me write the definition. Let n of t be a zero mean Y-stand stationary process with, let's say, autocorrelation Rn of tau, or power spectral density equivalently as n of f given as, let's say, in the following sketch. Okay, so I need a sketch. So let's use this part for the sketch. Well, so this is the sketch for the power spectral density. So let's say that this is something like that. Let's sketch this better. So this is A, let's say, one more time. Something like this, power spectral density, given like that. Now, observations number 1, question. Can we observe that the process n of t is zero mean from, let's say, S n of f, let's say sketch. Well, it says zero mean. This is just something extra. We are thinking, can we observe it? Whether I can, do I need this information if I have this sketch like that? That is, okay. So how can I observe this? The answer is, well, assume n of t is not zero mean, let's say. Okay. Then what happens? Now n of t is, let's say, a value such as, let's say, gamma plus a zero mean process. Let me write it like this, zero mean. So this is the zero mean process. Do you agree? So gamma, n of t is not zero mean. So gamma is not equal to 0. So this is a real number. Oh, well, it can be complex number, but okay, real number. That is it. Now, if I have this, what is Rn of tau? If I calculate this, well, many times we have done such calculations. So do you agree that this is Rn, the zero mean version of tau, plus gamma square? If I do that product, I have that. If I do this product, I have 4 terms, 2 terms over here, 2 times 2, 4 terms. 2 of the terms are over here. I have gamma times n, but this is zero mean, so cross terms will be equal to 0. So if I take the Fourier transform of this, what do I get? So Sn zero mean version of f plus, so this is the deal. Okay. So if there is an impulse at frequency is equal to 0 due to non-zero mean. But let's pay attention. This is this power spectral density. I mean, this is what we do all the time, but this power spectral density. So if this is like non-zero mean, there will be an impulse over here. Okay? Clearly, at origin, there should be an impulse. If you don't see an impulse, well, I don't need this information, perhaps, if I that sketch at the very beginning. Okay? Very good. So why am I writing here power spectral density? There are some other, it's called covariance. It's not the power, but covariance spectral density. You calculate the covariance function and take its Fourier transform. Covariance function. Do you remember? We had covariance functions also. Covariance function. You can also take its Fourier transform. We are not using that one in this course, but it has also importance in some studies. So of course, for the covariance function in spectrum, in Fourier transform, since you are subtracting the means, there will be never an impulse over here. But if you are talking about power spectral density, autocorrelations Fourier transform, now you can say that this is zero mean because I don't see an impulse over there. Okay, good to know. I mean, this picture tells us something about the mean also. But this was like a distraction for us. What was our goal? Our goal is representation of this bandpass process, random process, in terms of its Lowpass equivalent. Okay, so this was like something about this power spectral density, but let's go proceed over here. So what's the question? We would like to find an equivalent Lowpass random process like we did for the deterministic signals to represent bandpass, you see the spectrum, random process n of t. Okay. So clearly, for example, if you construct a filter in this band, so output power of that filter will be equal to 0. LTI filter only capturing the components of this random process in this band. Output power of this filter will be equal to 0 because there is nothing to capture, obviously. So all frequencies, you don't see anything. So only the frequencies in between f1 and f2. That filter will be producing a non-zero output. Okay, that is the case. So steps. So number one, it's not very surprising. Generate analytic process. So what do I mean by this? N plus process N of t plus j this. Okay. So right now these are random processes. This is a random process. This is another random process. Okay. So what do I mean by this? N hat of t is Hilbert transform of n of t, but this is a random process. So this is the output process. This is the output process, this. But luckily we know how to study, filtering of random processes and so on. Okay? I can do such calculations. So we will deal with this. It's not very complicated, you will see. Number two, generate the Lowpass equivalent process. So this is N, Lowpass equivalent. This is the analytic signal, or analytic right now process. Okay. So I need to shift this to the right as we did. Sorry. Is it right? To the left. So I need a minus sign over here. 2 pi fct. So what is fc over here? fc is a chosen representation frequency for the Lowpass equivalent. I am free to choose this. Okay. So my Lowpass equivalent has this as my parameter. So this moves my bandpass signal to the origin and so on. Okay, so that is the end. So how can I do this? And first of all, since this is a random process, what kind of operations are we implementing over here in step number one, step number two? Because it's exactly the same process that we are doing for deterministic signals. So what's going on? So let me think. So let's see. Step number one. So on step number one, so let me draw the following. If I have n of t over here, then let me sketch the Hilbert transform. 1 over pi t. Am I right? This will be the, whatever n, it will be Hilbert transform will be there. So we are over here. So how about this? But let me multiply by j at some point. It's a little strange looking, but multiplication by j. And then this is this. Am I right? So I'm adding them. So this is n hat of t times j, n hat of t times j plus n, and so on. Well, you can think that now this is like a deterministic operation. Whatever n I have over here, it's just filtered and then summed up. This will be my output. So in terms of random process, what happens? Well, you generate this random process somehow from this sample space. Do you remember such descriptions? You generate a realization of this, maybe random process. Maybe if it is like random phase cosine, it will be a cosine with a starting phase random. Okay? So it's like process like this. At the end, you get another random process or realization of another random process, because there is a realization at the input. After this kind of an operation, there is another realization for this process. So what is driving this process is the basic randomness of this initial sample space, isn't it? This is the sample space. So if I repeat this, there will be another realization, okay? It's like process like that, so I get another random process. This is the way, so the only thing that is random over here is at this initial sample space. The rest is, you can see that, is fully deterministic, okay? So this is like a mapping from this sample space, essentially, to this sample space by some deterministic operations. So everything is deterministic over here. Well, how about this then? So if I can, that's fine. So this should be something like a filter in my opinion. So let me write this. N plus of t is equal to n of t plus j n hat of t. Am I right? So if I take its Fourier transform, this is capital N f. So this n of f plus j. So this is the Fourier transform of, let me write it over here, minus j signum f, not x this time, n of f. So this is the Fourier transform of n hat of t. Am I right? That is it. So actually we have done this before, obviously. This step number 1 is it's the same step that we do for deterministic signals. I get this. Am I right? J minus j, get 1, and I have this. So this is equal to, I have the following 2. Well, okay, at this point, that's good enough. So that is it. Now from here to there, then the transfer function is this. I may consider that from here to there. Now this is my green box. Okay, so this green box has transfer function of h of f, which is this h of f. Okay, 1 plus signum f. So this becomes an LTI filtering operation. Okay, with frequency response 1 plus signum f. So I can find everything that I want for this output process. But before that, maybe let's remember some basic facts. We are almost done. Now, do you remember the following? If I have x of t, h of t, y of t, this is y sense stationary, okay. Then this is LTI, obviously. If I write anything like this, this is impulse response. That means impulse response of an LTI system. Okay. Otherwise, impulse response is not even well defined. Okay. Well, this is the output. So what we know? Number 1, x of t, y of t, jointly y sense stationary. Okay, previously we have derived this. Number 2, our y of tau is equal to our x of tau convolution. We have convolution relations like this. This is the output process autocorrelation. Okay. We can write input-output cross-correlation. Okay. So this is also in your notes. It is this. I can also write it differently. Yx of tau. So this is xy, yx. Okay. So conjugate is on the second one. Okay. So this becomes, now you can see that y is conjugated over here. Since y is the process version of x, it contains h. Clearly there is conjugation over h for this one. Now there won't be any conjugation over h because y is the first variable. So this would be like h of tau Of course, there is some little minor differences, but that's it. Rx of tau. What else? Now, let me write over here, number 3. The power spectral density it is the Fourier transform of this. So, this is the Fourier transform. How about this? Sxy of f, Sx of f times this Fourier transform is this Fourier transform has the conjugate of h of f. Hyx of f, h of f, Sx of f. Okay. So these are also Fourier transform related and Fourier transform related. Okay. So we know this from our earlier derivation. So let me write this, put it over here, like our cheat sheet. Okay. So let me call this like our basic facts. Okay. These are our basic facts. So if this is Weisstein stationary and system is LTI, output is also Weisstein stationary, jointly Weisstein stationary even with the input, and I can calculate output autocorrelation, cross correlations, etc. from these relations. Very good. Now, what do I want to do? Now I want to calculate this thing. So this is step number 1. So let me use this part. Then, let's remember, I want to calculate the power spectral density of this, let's say. Then, and plus of T process has power spectral density, which is S and plus of F. So how can I calculate this? So input is processed by this filter. S n of f times, let's say h of f as we have defined magnitude square. Okay. So this is the filter in green, I guess. So this is 1 plus signum f. So if I sketch this function, so it's taking the value of 1 over here, 0 over here, 2 over here. It is this function is over here. Okay, 1 plus signum f. Now how can I sketch this? Now this becomes 4 times S n of f. 2 times 2 is 4 for positive frequencies. There is something going on at 0 frequency, but let's do not worry about 0 frequency. And 0. Okay. I mean, there is nothing special about this 0 frequency, but for the sake of Fourier transform discussions, you know, the value of this function at a point is not important. The value of the function is not at a single point, at an isolated single point is not important. Okay, so this is the end. So what do I mean by this is the end? Well, previously, I have erased this unfortunately. We had Sn of f. It was in between f1, f2, minus f1, minus f2, the value of a. Now, we are over here. We are at step number 1. At the end of step number 1. We have reached the following. Another random process. Let's erase this part. But maybe I can keep this because it's step 2. So at the end of step number 1, the positive frequencies are retained and all negative frequencies are nulled, and this becomes, this time for A, S and analytic signal F. Well, this analytic signal is actually of great importance in complex, let's say, variables also. It has some other applications in complex variables. It's a big deal. As you can imagine, if something is called analytic, that means that it has some additional properties. But we won't be worried about those properties, okay? Analytic signals properties. This is just for our purposes, you know, negative frequencies are null. Definition, something like that. Okay, so we need to do the step number 2. So let me reserve this. At the end of step number 2, we will be sketching, hopefully, Lowpass equivalent process power spectral density. So how can I do this? So this is the end of step number 1. So we are going to step number 2. Step 2. Now, I would like to discuss this. Now, my Lowpass, this process, should be shifted to the origin. So this is a random process, okay? So I'm multiplying by a random process by a function. So this is another random process, okay? That will be called Lowpass equivalent random process. So you may wonder whether it will be a Weissan stationary process or not, because since this is like LTI filtering, because of our basic facts, I know that this will be Weissan stationary. But after this operation, do you think this will be Weissan stationary? If it is not Weissan stationary, then its power spectral density will not mean anything, because it doesn't have an, you know, autocorrelation in single variable. So this should be Weissan stationary in order to this thing make sense. Okay. So let's be patient. Then let's see. R Lowpass equivalent as a function of hopefully tau. Hopefully it will be only function of tau. So let me do this. And Lowpass equivalent t and Lowpass equivalent t minus tau and conjugate. Am I right? So I should do this. Let's see. Expected value of. So this is my random process. This is the analytic. Wow. Let me write it over here, not to get confused. This one, as it is. Do you agree? But don't forget the conjugate. Well, it has to be present over here. So this is, let me put it in red then. Okay, this is the same conjugate over there. So what do I have? So if I do this product, so this becomes after conjugation plus J2 pi fct with plus, J2 pi fct with minus. Very nice, t's cancel, very happy. So I'm seeing the following. This is equal to expected value of so everything goes very right, as you see. Am I right? So this is with plus, so I have something like this. Am I right? But what is random over here? There is nothing random about this part. Take it out. But we know that this is Weissan stationary. Well, its power spectral density is this. Then I have the following. R n plus of tau, this part, times e to the minus j 2 pi fc of tau. So everything goes very right, as you see. So do you see a t dependence over here, not a function of time? So initially there were t's over here, but they got cancelled at this step. Okay, so not a function of time. So this Lowpass equivalent process after the step number 2 is y-sans stationary. So of course it is zero mean process. Everything is zero mean. By doing these kinds of operations, everything remains at zero mean. Okay. So zero mean, why do I need? For y-sans stationarity, I need stationarity in the mean and stationarity in the autocorrelation, as you see. Okay, so how about this? Now it's Fourier transform. S, Lowpass equivalent in Fourier transform. This is where we need this modulation property. So this is modulating towards, less frequencies, smaller frequencies. Okay. So this is shift towards the left. Okay. So I get that. Very good. Very happy. It's almost like the same thing for the power spectral density. At the end of step number 2, I should be shifting this Sn plus of f with 4a, okay, to the origin. But I should select my Fc. This is called the representation frequency. One more time. So let's select representation frequency just for the sake of representation. Let me select this like this is my Fc. Okay. So this Fc will be moved to the origin. This will be 0. So then I have 3a value over here. So this will be reaching 4a over here. And it will be something like this. Okay. So this is F2 minus Fc. This is F1 minus Fc, and so on. This part, this point on the frequency axis, I have that. That is it. So Fc is somewhere over here, minus Fc is somewhere over here, and so on. So as you see, one important thing one more time about this Lowpass equivalence, this Fc has nothing to do with this bandpass signal, bandpass process, etc. I can select Fc at this point. It depends on how much I want to shift, okay, to the origin. It's not related with the process. Of course, if this is like symmetric and so on, it may have some practical applications. You can select the symmetry center, etc. But I can select this in any way that I want in general. So that is the end. So this is the end of, Lowpass equivalent process finding. That is the end. But let me write a few comments. So at the end, what did we do? So if you are explaining this to your little sister, let's say, what you do is at the end of this discussion, you erase this, multiply this part by 2, then you shift this to the center by Fc. That is it. Okay, there is nothing else. So what are we talking about right now? This is not a deterministic signal. This is the power spectral density of a random process. Okay, the only difference is that power spectral density of a random process. So notes, number 1, we have seen that the Lowpass equivalent of a bandpass y-sans stationary process is also y-sans stationary. So I'm talking about this Lowpass equivalent, and has a power spectral density S Lowpass F as can be found very similar, if not identical, to the process of finding deterministic signal Lowpass equivalence. Everything goes very right. That is the issue. For example, over here, y-sans stationarity is preserved. this becomes a filtering operation, etc. and etc. Steps 1 and 2 goes very right. Find Lowpass equivalence. This is number 1. This is our observation number 1. Number 2, so in general, an LPT is a complex valued process. No surprises. Sometimes this Lowpass equivalence, they are also called complex envelope of the signal. There is another name in telecommunications. So it's not called Lowpass equivalent, but I think Lowpass equivalent is better because Lowpass is very something intuitive for electrical engineers, and equivalence that is what we are seeking in many problems. Like in every problems, we are trying to find simpler and equivalent circuits, let's say. Okay. Things like that, or equivalent models of a mechanical system, things like that. So Lowpass equivalence is a better name in my opinion, but it's also called complex envelope. In case you see this, it's also called complex envelope. In general, Lowpass equivalent is a complex valued process, i.e. it is something like this. This is called the in-phase, the real part, in-phase component. One more time. This is, of course, a random process right now. This is the quadrature. Quadrature means a quarter. Quadrature phase or quadrature component. So why do I say so? Because there is like 90 degrees phase shift. So again, from circuit theory or basic electrical engineering. So if you have multiplication by J, so this refers to 90 degrees phase shift. Quadrature means lambda over 4, okay? This is like T over 4 in seconds and so on. So a quarter of a period, quadrature phase component. So in general, this is a complex valued process. I have this. The next question is, finding, let's say, S and I, F, S and Q, F, so real and the imaginary parts, and let's say S and I and Q, F, cross correlation, Fourier transform of their cross correlation of these two random processes. Again, this won't be very complicated. It will be, again, a shifting operation, something like that, but we have to derive that. So we will do that derivation in the next lecture after the break. Okay.